YouTube. All right, thank you. So, hi everyone. I'm delighted to introduce Dylene, Agda, Souza de Barros, who's going to be speaking to us today about some half homomorphisms of some types of loops. So, take it away, Dylene.
Okay. Well, thank you. Thank you very much. Thank you for the organizers of the seminar, especially Charlotte, who has invited me. And it's a pleasure to talk to you this afternoon. And well, we start defining what is a half homomorphism. Well, if we have two binary algebras, L and L prime, we say that a map F from L to L prime is a half homomorphism if f of x star y belongs to that set. See, let's point to that set. Okay, forever x and y and L. So in the case that forever x and y and L of x and y and L, f of x star y is equal to f of x, f of y, we have a homomorphism. And in the case of forever x and y and L, f of x star y is equal to f of y, f of x, we have an anti-homomorphism. And we say that a half homomorphism is proper if it's neither a homomorphism nor an anti-homomorphism, okay? In 1957, Scott proved that there's no proper half homomorphism between cancellation semigroups. In particular, there's no proper half homomorphism between two groups. But in the same paper, he gave an example of a loop of order 8 that has a proper half automorphism. So Scott results cannot be generalized for all loops. Here, it's the Cayley table of the loop that the example that Scott gave, and the proper half automorphism that he gives is the transposition 7-8. Okay. Well, in the case that there's someone that doesn't know what is a loop is an unempty set L if a binary operation that set that forever a and b in L, the equations ax equal to b and ya equals to b have unique solution, and there exists a unit and a neutral element for this binary system. If you put the associative law in this definition, we have a group. So groups are precisely associative loops. As an example, we can consider this L prime given by this following Cayley table, and there's every linear equation have unique solution because in this table every element in each row and each columns every element appears only once, and it is not associative for this example. Okay. Okay, so what we know, since the result of Scott, since the result of Scott, there is no point to study half homomorphism, half isomorphism, half automorphism between groups. So what do we know about half isomorphism between loops? In this slide, we can see that when we have a half isomorphism between from the loop L to the loop L prime, and somehow this half isomorphism pull some properties of the loop L prime to the loop L. For example, if H is a subgroup of L prime, then F minus 1 H is a subloop of L. If H is commutative, so F minus 1 8 is commutative and isomorphic to 8. Half isomorphism preserves identity, and if in L prime every element has a two-side inverse, so this property also holds for L. So every element of L has a two-side inverse, and the inverses respect this property. Okay. Other properties that we have. If you have a half isomorphism between these two loops, L and L prime, and L prime is power associative. So the half isomorphism behaves well according to powers. Also, L is power associative. I didn't mention it, but power associative means that every element of the loop generates a cyclic group. And if X in L has finite order, so the order is preserved by the half isomorphism, okay? One thing that we have about half isomorphism is that we have F from L to L prime, a half isomorphism. But the same, we cannot say always by the inverse. Not necessarily the inverse of a half isomorphism is a half isomorphism. So for that, we define a half isomorphism be special. So a half isomorphism between two loops is special if the inverse is also a half isomorphism. And the characterization for that is if we have a half isomorphism between two loops, F is special if and only if these two sets are equal, and if and only if you have two elements that commutes, so that half isomorphisms behave like an isomorphism. Okay? Just show an example. Let's see, let L be the cyclic group of order 6, and L prime the loop of the previous example. So we have these two Cayley tables, okay? F, the identity, the f of x equal to x is the half of isomorphism from L to L prime, but inverse is not, because if you see that 66 is commutative, but L prime is not. Okay, so that's an example that half isomorphism that's not special. Okay, but if we are dealing with half automorphism and finite loops, there's nothing to worry about. So every half automorphism of a finite loop is special, and as a corollary of that, the set of all half automorphisms of a finite loop is a group. So we have the group of all half automorphisms of a finite loop. We have the group of automorphism of the a finite loop. In the middle, we have G, the group generated by all non-proper half automorphism. Okay, so what we do when we study what we are doing when we study half automorphism so far, we have two types of problems. You choose a loop and you try to prove that the Scott results extends for that loop, or you take a look, see that there exists proper half automorphism of that loop, and then you try to describe the group of half automorphism of that. That's basically so far the two how can I say, two ways to research in that area so far. Okay, so for that, I mean, you choose a loop as you saw in few slides ago. The definition of loop is not very rich or something like that. We have to put some other identities to that loop to make the structure more how can I say? I forgot the word in English, sorry. To make more doable to the structure. So,
Excuse me. Excuse me, Dylene, may I interrupt? You just mentioned that
sure.
you saw something a few slides ago. I don't see any slides. I do see that you're writing on a tablet. Is there a way to share your screen with us so that we can see what you're?
Oh, I'm not screaming? Can you,
I
you're
don't,
not
I see
seeing my
you.
slide?
I see you, but I don't see the slides. Is there a way to
I
share those?
I'm seeing the slides.
Okay, then I'm sorry. It's my
Yeah,
mistake. Okay, it's my mistake. I don't see why I don't see them then.
perhaps on a different screen.
Oh,
Uh,
I'm seeing the slides.
I see them now. Okay, thank you. Thank you. I see
oh,
them now.
okay, okay.
All
Well, so, um, okay, so let's from here. So we say a loop is a Mulfang loop if this identity holds for every x, y, and z in L. We say that a loop is a left ball loop for this identity. I mean this identity here. A right ball loop for this identity. Okay. And just an observation, just a remark. If a loop is left and right ball loop, so we have a Mulfang loop, and we have an automorphic loop if all inner mappings is an automorphism of automorphisms of the loop. So by inner mapping, I mean all multiplications. The group of multiplication of a loop is the group generated by all translations, right and left translations. So that fits the identity. Okay, so I display that kind of the types of loops for my next slide. So when does Scott result holds? Now, for Mulfang loops of odd order, so there's no half automorphism, no proper half automorphism of Mulfang loops of odd order. What I mean that every half automorphism of Mulfang loops is either an automorphism or or an anti-automorphism. For finite automorphic Mulfang loops, you also have the same result. If Q is a Mulfang loop such that the factor of Q to its nucleus is 2 divisible, then every half isomorphism from Q is either an isomorphism or an anti-isomorphism, and there is no proper half automorphism of an automorphic loop of odd order, okay? And in the other way, we have conditions for existence of proper half automorphism of certain Mulfang loops of even order, including chain loops. There's a description of a half automorphism group of a class of automorphic loops of even order. There's a description for half automorphism group of some chain loops. There's a half automorphism, the description of half automorphism group of some ball loops. And there's some the description of half automorphism group of some code loops. Okay. From now, I'm going to discuss about this result. Okay. This is a work that I did in collaboration with Souza dos Anjos. Okay, so let's see about ball loops. A right ball loop is a loop that satisfies the right ball identity, and the left ball loop is a loop that satisfies the left ball identity. And as I said, if they satisfies the two of them is a Mulfang loop. So for a ball loop that is not Mulfang, there's no anti-automorphism. So because if there is an anti-automorphism, so the loop is isomorphic to its opposite. So a right bow loop is isomorphic to a left bow loop, so it's be a muffin. So there's no anti-automorphism for a bow loop that is not muffin, okay? And so if we are searching for half-automorphism of a bow loop that is not muffin, so this half-automorphism is either an automorphism or a proper half-automorphism, okay? Okay. To construct the class of bow loops that we are dealing with, we are using that proposition for Fogel, Michael Kenyon, and J.J. Phillips. So let G be a group, H a subgroup of G, and B a right transversal of H in G. And we are supposing that B is a twist subgroup of G, then B with this operation is a bow loop, is a right bow loop. I mean, from now on, I'm dealing only with right bow loops because they're very similar. So I'm choosing dealing with right bow loops, okay? So this right transversal of this subgroup in G is a bow loop. There's a converse of this proposition, but the direct implication that matters for us. Okay, so let's construct the group G. We start with an abelian group M, okay, and construct the generalized dihedral group of M, okay, and take G as the direct product of Z2, Z2, Dm, okay? And we choose H as this subgroup, okay? So that's all ingredients that we have. So this set B is a right transversal of H in G, contains the unit, and is a twisted subgroup of G. Okay, so according to the proposition that I just displayed, this set is a right bow loop with the following operation. Okay, it's kind of confusing because of this arc, but it's not difficult. But we can drop all these R and use a simpler isomorphic construction. So take M, an abelian group. We define LM as Z2, Z2, M, the direct product. And we define the following operation, okay? So if these two components, if these two components is equal to 0 in this right factor, we just use the direct product. If it's not, we use kind of direct product, but we use x minus 1 instead of x, okay? So another way to see that loop, we exchange Z2 by the Klein group. So we have LM, K times M. M is a finite abelian group with exponent greater than 2. I'm going to explain that in a bit. And then K, the Klein group. So this set LM with this operation, if is a bow loop, which is not a muffin loop. Again, here, if you have not the identity in this right side of in this right factor, we use x minus 1 instead of x, okay? This exponent greater than 2 means because if M is an elementary abelian 2 group, then LM is also an elementary abelian 2 group, so that x minus 1 plays no role here. So if M is not an elementary abelian 2 group, so LM is a non-associative, non-commutative bow loop, which not moving. And that loop is the loop that we are dealing to find the group of half-automorphism. Just to say, all this story began when, using GAP, we find a GAP library, we find a ball loop with order 12, and we find that, but I mean, it's simpler, the code is simple, but it's not so easy to run. We discovered a proper half-automorphism of that loop. So, and then, well, let's find others and see what's the group, what is the group of half-automorphism, okay? And then we start with this example that I put in the end of these slides, and then we saw that particular ball loop of order 12 is an example of this kind of ball loop that we construct here, okay? So let's see let's talk about half-automorphism of this ball loop. So recall that a half-automorphism of Lm is a bijection of Lm, such that we have this for ever x and y in Lm, okay? So the first thing that we saw, that if we have the 1m, okay, that's because Lm it's Km, so 1m is a subloop of Lm. If you have 1m, so F preserves this subloop, okay? So if you have F of 1x, it can be written as 1 F2 prime of x, on F2 prime of x belongs to m. And what we saw is that F2 primes is an automorphism of M, okay? So every time you have a half-automorphism of Lm, it fixes this half-automorphism, fix that subloop, and this function in M is an automorphism, okay? For 1K, it's not so easy, because by the way that we define the product in Lm. So for K1, so F of K1 is a subloop, isomorphic to K of order 4. And so we decided to consider that set calligraph HM of all subloops of Lm that isomorphic to K that is disjoint of 1m, okay? So if F in a half-automorphism, so F of K1 belongs to that HM, and there's three possibilities for that. If we have an H in that HM, or H is just K1, or H is that form 1, 1, AX, BX, C1, and ABC forms the non-identical elements of the Klein groups of order 2. Remember that I think that Klein group is 1, A, B, C here. H is of that form. 1, 1, AX, BY, and C, XY, okay? And XY, two different elements of M of order equal to 2. In particular, if M has odd order, so that HM is only K1, okay? So M of odd order, so F K1 is also K1, okay? Okay, so as a corollary of that, we have, as a corollary of that, we have that if F is a half-automorphism of Lm, then there exists a unique F prime an automorphism of K, and X and Y in M with order less than or equal to 2, such that Fy1 is F prime of A, and something here that we call alpha xy of A, on where alpha xy of 1 is 1, and alpha xy of A is X, alpha xy of B is Y, and alpha xy of C is XY. Okay, we choose this Fy by the elements that appear over here. Okay, so the mapping alpha xy is a homomorphism from K to M, and one alpha xy A is an essential element of the loop forever A and K. Okay. What we have right now? We have how F1M works, FK1 works. So using that, every element XA in LM can be written as A11X. Here it's important that we put 1 over here because it's make the product in LM simpler. There are F prime automorphisms of K, U and V in M, such that FA1 is F prime of A, alpha UV and A, with U and V with order less or equal to 2. For A not equal to 1, we have FAX. We just make this computation over here. So if F if A not equal to 1, so we have this calculation over here, and here we have something different of 1. So F of AX, after all this computation, we have this option or these options using X minus 1 instead of X here. Okay, so that's just using the product of the loop. Okay, so just some comment to make here. When we were working that project, that was very difficult. We struggled to find easy notation, a good notation. While I was preparing that seminar, I realized that I think we failed, but I mean, I'll try to make some notations simpler over here, okay? So for F prime an automorphism of K, F2 prime is an automorphism of M, U and V and M elements of order less or equal to 2, we define 2 other functions. Capital F plus with these 4 parameters in X way, it's in X in AX is just F prime of A, F2 prime of X, alpha UV of A, okay? And capital F minus with these 4 parameters, we define in AX S. This way, if A is equal to 1, and we remember that if A is not equal to 1, we have to use X minus 1 instead, okay? And to making the notation a little bit easier, we use F plus and F minus with the parameters U and V instead of this huge notation over here, okay? Seeing that, what we had, F plus is an automorphism and F minus is a proper half-automorphism of Lm for every U and V in M, okay? More than that, if G is an automorphism, so G is a G plus. For some, G is a G plus. And if G is a proper half-automorphism, then G is G minus, okay? So we could split every half-automorphism of Lm in a part of which is an automorphism is in a part of is a proper half-automorphism, okay? So let me clarify that automorphisms are half-automorphisms, a particular case of half-automorphism. So we just, in general, we have an automorphism with a proper half-automorphism over here, okay? So with that, we have that the group of half-automorphism of Ln is simply T2 times the group of automorphism of Ln. This C2 comes from this x minus 1 because we have to exchange x and x minus 1 depend of A. So this C2 part comes from this x minus 1 that happens here, okay? So to complete this study, what we did was describe the group of automorphism of this loop. So, for example, remember that for every we have F capital F plus with these two parameters, an automorphism of K, an automorphism of M, and two elements of M that order less or equal to 1. We define that A as all capital F plus when this U and V is equal to 1, okay? So we have that A is isomorphic to the direct product of the group of automorphism of K and the group of automorphism of M. So in the case when M is odd, then there's no element of order 2 in M. So this A is exactly the automorphous group of Lm. So we have this theorem for Lm, K times M, the ball loop, on where K is a Klein group and M is an abelian group of odd order. Then this automorphism group of Lm, it's S3 times the automorphism group of M, and the half automorphism group of Lm is C2 times S3 times automorphism group of M, okay? So in the case that M has even order, so it's a little bit more complicated, but not so much. We decompose M as this product of these two cyclic groups, and M1 when M1 is a abelian group of odd order, okay? We use that set H of all x in M with order less or equal to 2. We have that H has 2 to the S elements, when S is the number of these components. And we define that B like capital F plus, but instead of use the parameters F and F prime, we use only the identities of K and M, okay? So the only parameters that may vary here in that F plus, it's X and Y, for X and Y and H. So we have that B isomorphic to the direct product H times H. And this set B is a subgroup of the automorphism group of Ln, okay? Also remember that group A, that we use that the capital F, F prime, F2 prime, 1, 1. That's the capital A, that's the calligraph A. So this intersection is just 1. And we have this counting of the number of elements of A and B, okay? So we have 2 to the S, the number of elements of automorphism group of K, and the number of elements of automorphic group of M, okay? So the automorphism group of L, M, when M has all even, is that product A, B is equal to BA. We have these properties over here, okay? And then using that, we have the automorphic group of Lm is just the same direct product of A and B that we have here, okay? So for a finite abelian group of even order, we have this result for the automorphism over here. This result for automorphism group of Ln, that loop that we define in K time n, then the half automorphism group of Lm is C2 times this semi-direct product, okay? And A is just S3 times the automorphism group of M, okay? To illustrate that, so that's the example that we start using gap when we use M equals to C3. So Lm is a non-associative Ball loop of order 12, and we can find it in the gap library, like right Ball loop 12, 3. There's 3. One is Mulfang, one is a Ball loop there's no proper half automorphism of that loop, and other ones that since out M is C2, we have this counting for that. So Lm has 24 half automorphisms, from which 12 are proper. So that's why we could investigate that in gap, because the group is not very good. It's not very big. So it's good to deal that with gap because it's not very big. So that's the Cayley table for that group. And we can express all the automorphism and all the proper half automorphisms by this permutation using that Cayley table. And another example is when we take M, the abelian group C4 to C2, it's the small group A2 in gap. So Lm is a non-associative, non-Mulfang Ball loop of order 32. And out M is D8, and then we have this count. So this loop Lm has 1536. I have language issues for huge numbers, and sorry about that, but we have morphisms from which the half of that is are proper, okay? And that's it. Thanks for the attention. I mean, I think I spoke so fast, sorry. That's it.